Enough about the parts of the stereo microscope. Now let's learn how to use one. The learning objective of this section is to adjust, use, and maintain a stereo microscope. First, remove the microscope from its storage location. When not in use, any microscope should be protected from dust, usually with a plastic dust cover. Always carry a microscope with two hands. One hand should support the base and one hand should steady it by its vertical arm or column. A microscope is heavy and needs a solid table to support its weight. A solid support will also reduce vibration. Vibration reduces image clarity. If you are going to use a microscope for a long period of time, use a chair that allows you to comfortably look into the ocular lenses and easily adjust the microscope and object. Check that the outside surfaces of the ocular and objective lenses are clean. That is, that they are free of dust and oil. Eyelashes and eyebrows often transfer skin oils and eye makeup into the ocular lenses. Such materials should be cleaned off with a lens cleaning solution and lens paper. The cleaning solution consists of water, alcohol, and detergent. Lens papers are made of fine fibers that do not produce lint. Never use facial or other tissues on a microscope lens, as they may scratch the glass or remove the special lens coatings. Objective lenses seldom need cleaning unless you touch the lenses with your fingers. You should not remove any lens from its housing for cleaning the internal surfaces. Leave that for an expert. Now we will use the microscope to view an object. To start with, use a flat piece of newspaper or a series of printed A's or E's as an object. Plug in the light source. Adjust the microscope lamp so that the object is illuminated evenly. Move the objective lens with the lowest magnification into position. The lowest objective lens is labeled with the lowest number, in this case 6.4. Look into the objective lenses and move your head up and down until you see the largest image. If you use eyeglasses, you may choose to wear them or remove them. To make the interpupillary adjustment, move the ocular tubes together or apart so that you can see only one circle of light, not two circles. To make the diopter adjustment, first determine which one of the two ocular lenses is adjustable. Usually, this is easily detected by the presence of a grooved or knurled collar. First, close or cover your eye on the side of the adjustable tube, and using your open eye and the focusing knob, bring the image into focus. Then, close or cover the eye on the non-adjustable side and open your other eye. Use the knurled knob on the adjustable ocular tube to focus the image. Open both eyes to see the object in complete focus. The image that you see through a stereo microscope is upright or erect. A pair of prisms in the body of the microscope does this. When you move the object to your left, the image moves to the left. When you move the object up, the image also moves up. Such properties make a stereo microscope ideal for dissecting purposes. In fact, many people call such microscopes dissecting microscopes. Move the next higher objective lens into position. Note that with increased magnification, the area of the object that you see is decreased. What you can see in the circle of light of a microscope is called the field of view. The size of the field of view decreases with increased magnification. The learning objective of this section was to set up, adjust, and use a stereo microscope. This included cleaning the external surfaces of ocular and objective lenses, adjusting the light, adjusting interpupillary distance, setting diopter adjustment, and focusing. Be sure to clean your ocular lenses and replace the dust cover before storing your microscope. The major disadvantage of stereo microscopes is that they are normally limited to magnifications of about 50 times. For higher magnifications, you have to use a compound microscope. The learning objective of this section is to identify and describe the functions of the basic parts of a compound microscope. Just as there are many kinds of stereo microscopes, there are many kinds of compound microscopes. However, each of them has a base that supports the microscope and an arm that connects the base to the rest of the microscope. Although the stage of a stereo microscope is usually completely solid, the stage of a compound microscope has an opening, a hole, for light to pass through. Stage clips are often used on stereo or simple compound microscopes to hold a microscope slide on the stage and yet allow you to move it manually. In advanced compound microscopes, a mechanical stage is used to hold the microscope slide and move it from side to side and back to front. With the numbers on the side and back of the mechanical stage, you can repeatedly find the exact position of an object on a slide. A vernier scale allows references to 1/10 of a millimeter. All compound microscopes use transmitted light. Simple compound microscopes do not have a built-in light source. Light is directed to the lenses by a mirror. In this type of microscope, use the flat side of the mirror if you have a condenser and the concave side if you don't. Angle the mirror to evenly illuminate the field of view. If your microscope has an internal lamp, it is usually turned on and off with a sliding lever or a rotating knob. A condenser is a third optical component of a compound microscope. Its purpose is to gather diffuse light and concentrate or condense it into a narrow cone in the plane of the object. This improves the effectiveness of the objective lenses. A condenser may be fixed in position or movable with a knob. Generally, with the higher magnifications, a condenser is moved closer to the object. Closely associated with the condenser is a device for limiting the diameter of light entering the condenser. The usual mechanism is an iris diaphragm. An iris diaphragm consists of a set of thin overlapping metal leaves that can be moved by a lever to form a continuously adjustable aperture. Generally, the iris diaphragm is opened more widely with objective lenses with higher magnifications. Closing the iris diaphragm increases contrast. The iris diaphragm of the condenser should not be used to adjust the light intensity. Light intensity should be adjusted by decreasing the voltage to the lamp or adjusting an iris diaphragm on the lamp. Generally, with higher magnifications, you will have to increase the light intensity. There are two focus adjusting knobs on a compound microscope, a coarse adjustment knob and a fine adjustment knob. The coarse focusing knob always has a larger diameter than the fine. Use the coarse one first to get the objective approximately in focus, then use the fine one. The body of the microscope holds the lenses. Compound microscopes have 2 to 5 objective lenses mounted on a revolving nosepiece. Note that as the magnifications of the objective lenses increase, the physical lengths of the lenses increase. This causes the working distance, the space between the object and the objective lens, to decrease. In stereo microscopes, the working distance is very large, several centimeters. In compound microscopes, the working distance is very small, at most a few millimeters. Today's microscopes are usually designed so that the highest objective lenses cannot break regular slides. However, at higher magnifications, it is possible to break thicker slides. Such slides are usually called thick mounts. When using higher magnifications with such slides, focus the object by starting with the objective lens close to the slide and then move the lens away from the object. Higher objective lenses have smaller diameters and so smaller fields of view. So, before changing from a lower to higher magnification, position the object that you want to see in the center of the field of view. Good quality microscopes also have objective lenses that are parfocal with one another. Parfocal means that once you focused with the lowest magnification and switch objective lenses to higher magnifications, the object will remain in fairly good focus, perhaps needing only a minor adjustment of the fine focus knob. Compound microscopes can be monocular or binocular. Monocular microscopes have only one ocular lens, and so only one eye can be used to view the object. Still, to prevent eye strain when using a monocular microscope, both eyes should be kept open. Binocular microscopes have 2 ocular lenses. However, binocular compound microscopes have only one objective lens that can be used at one time, and so the image is only 2-dimensional. Stereo microscopes are all binocular because they must have 2 ocular as well as 2 objective lenses to create 3-dimensional or stereoscopic images. To make compound microscopes easier to use, most have inclined objective tubes. However, some older models have an arm and stage tilt mechanism. This is okay to use with prepared slides, but it is not very useful for wet mounts. Especially in compound microscopes, there may be a pointing device in one of the ocular lenses. Students and teachers use such pointers to help communicate with each other about what is being observed. Ocular lenses may also have a measuring device, often called the ocular micrometer. This will be discussed later in this video. Binocular compound microscopes have an interpupillary adjustment mechanism similar to stereo microscopes. Such compound microscopes also have a diopter adjustment mechanism. The learning objective of this section was to identify and describe the functions of the basic parts of a compound microscope, including base, stage, arm, body, coarse and fine focusing knobs, objective lenses, which are located on a nosepiece, ocular lenses, diopter adjustment, interpupillary adjustment, condenser, iris diaphragm, and lamp adjustments.